Hi guys, this video is all about estimating areas using geometry. So this may sound similar to what we have already been doing, but it's just a one-word difference actually. This time we're going to talk about estimating these areas using geometry. Everything that we have done so far, we've been able to make an exact triangle or rectangle or trapezoid or semicircle and find the exact area. But we need to talk about what happens when we have a function or a figure where we're not able to use exact geometric figures to find the area. So we're going to estimate it. And this is kind of what we did in class today with the Desmos activity. So you guys kind of looked at it. So hopefully this shouldn't be too bad to go through in the video. All right, so let's first talk about what this integral symbol means. So we know the integral from a to b of f of x dx means find the area trapped between the function and the x-axis from x equals a to x equals b. All right, so we've been doing that, but everything we've been finding so far has been exact areas because we've been able to, and we're able to do that using some of our geometry formulas. All right, but now we're going to start looking at what happens when we can't get these exact areas using geometry. So now we're going to start looking at estimating these actual areas. All right, and there are 4 ways that we use to estimate these areas. The first one we're going to talk about is LRAM. All right, LRAM stands for left rectangular approximation method. All right, left rectangular approximation method. We're also going to call this, or a lot of times on the AP exam, this is actually called the left Riemann sum. Okay, so either one of those, you have to know that that means we're finding the LRAM. All right, so let's take a look at this function here. I'm going to go ahead and call this f of x. And let's say we want to find the integral from 0 to 3 of f of x dx. So what we're going to look at here is we're going to look at 0, 1, 2, and 3 right here. And for this one, for the LRAM, we're going to start on the left. So in this case, we've got an interval from 0 to 1, 1 to 2, 2 to 3. So the left side there would be at 0 for my first interval. And I'm going to go up to the function and make a dot. And that left endpoint there now tells me the height of my entire rectangle from 0 to 1. All right, so it's called the left rectangular approximation method because we're using the left endpoint to find the height of our rectangle. All right, so again, if I'm going to look at the interval from 1 to 2, my left endpoint is going to be at 1. So I'm going to start at 1 and go up to my function. And then I'm going to go across to 2, and that's the height of my rectangle. My interval from 2 to 3, my left endpoint is at 2, so I'm going to go straight up to 2, or straight up from 2, excuse me, and that gives me the height of my rectangle from 2 to 3. So if you notice on this one, my intervals are all nice, they all go by 1. All right, so all of these rectangles have the same width, but the heights are determined by the left endpoints. All right, depending on our function, sometimes these approximations give us underestimates and sometimes they give us overestimates. You can clearly see that all of these rectangles are underneath our curve, so this one in particular would be an underestimate, whatever it happens to be. Okay? Let's take a look at RRAM. So RRAM stands for Right Rectangular Approximation Method. We also call this the right Riemann sum. Okay, so again, let's call this function f of x, and let's find the same integral from 0 to 3 of f of x dx. So again, we're going from 0 to 1, 1 to 2, and 2 to 3. But now, since we're doing a right rectangular approximation method, now I need to use my right endpoint. So on the interval from 0 to 1, my right endpoint is going to be at 1. So I'm going to start at 1 and go up to my function, and that creates the height for my first rectangle. Okay? Then I'm going to do the same thing on the interval from 1 to 2. My right endpoint is at 2. So I'm going to go straight up to my function, and then I'm going to go across, and that gives me the height then of my second rectangle. And for the third one, I go up to my function on my right endpoint, which is going to be at 3, and that gives me the height of my rectangle there. So again, the difference between the LRAM and the RRAM is where the endpoint, which endpoint helps us find the height of our rectangle. So LRAM, the left endpoint, helps us find it. RRAM, the right endpoint, helps us find the height of our rectangles. And you can clearly see that the RRAM in this situation is going to be an overestimate because all of these rectangles are now above my function. Okay? Moving on, we're going to talk about MRAM, which is the midpoint rectangular approximation method. Or the midpoint Riemann sum. All right, so for this one, instead of using either the left endpoints or the right endpoints, we're actually going to find the midpoint, and that's what's going to give us the height of our rectangles. So again, I'm still going to go 1, 2, 3. This is still going to be f of x, and I want the integral from 0 to 3 of f of x dx. Now the difference is going to be that I'm going to find the midpoint on my interval. So from 0 to 1, my midpoint would be at 1/2, and I'm going to go up to my function, and then I'm going to draw my rectangle with the height at whatever it happens to be at the midpoint. So again, let's do the interval from 1 to 2. So I'm going to find the midpoint, which would be 1/2. And I just draw a dotted line up to my function. And I know that it hits it right there. So that is going to be the height of my second rectangle. On the interval from 2 to 3, I'm going to find the midpoint and go up to the function, and that's going to give me the height of my third rectangle. All right, so we can see this one has a little bit above the function and a little bit below, so this one might be a little bit more accurate, but we don't really know without calculating, okay? Then we've got the trapezoidal method. All right, so let's remind ourselves that in order to find the area of a trapezoid, it's h over 2 times b1 plus b2. All right, now the trapezoidal one, what we're going to do is we're going to take both of our endpoints, so at 0 and at 1, and what we do is we connect those 2 points, and now we've made a trapezoid. It's a little hard to see on some of the smaller ones, so I'm going to keep going and hopefully it'll start to make a little bit more sense. But here's the height at 1. Now I'm going to find the height at 2. And if I just connect those dots, I made a trapezoid. And then I'm going to find my height at 3. And then I'm going to go ahead and connect those, and I made a trapezoid there. That one is probably the easiest one of the 3 to see. All right, we've got these two parallel bases, and then we've got this slant, and the height happens to be this subinterval right here. Okay, I know that kind of took a lot to explain, but I need you guys to understand the pictures. So the other thing I need you to understand here is that it's really important to remember we're estimating, okay? We are not able to get the exact answers here. These are all approximations. All right. The size of your subinterval matters. The subinterval is how wide you make your shapes. So whether we're talking about the rectangles or the trapezoids, the subinterval is how wide we make them. So you can see here we had 3 subintervals, and here we obviously have, what is that, 1, 2, 3, 4, 5, 6, 7, 8 subintervals, something like that. So we have more, okay? But you can see that the smaller the subintervals are, the more precise the area is. Okay, so the goal is usually to actually have more subintervals because we can see that this is getting closer to an actual area. This one is definitely a big overestimate. There's a lot of area above our function here. Okay, so let's look at what this actually looks like in some examples. So we have the graph of f of x equals x squared plus 3, so it's just a parabola shifted up 3. And we want to estimate the value of the integral from 0 to 4 of f of x dx. So for example 1, we're looking at RRAM, which means we're looking for the right endpoints to give us the heights, and we want 4 subintervals. Well, since we're going from 0 to 4, and we want 4 subintervals, that works out really nicely that we're just going to go from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Those are our nice subintervals, okay? So I'm going to go ahead and draw the graph really quick. If I'm going from 0 to 1 and I want RRAM, I'm going to go to 1, and that's going to give me the height of my rectangle. So that's going to be my first one. And then I'm going to do these in different colors so you can kind of see them. Then for the interval from 1 to 2, I want to go to 2, and that's going to give me the height of my rectangle. And then from 2 to 3, I want to go to 3 because that's my right endpoint, and that's going to give me the height of my rectangle. And then finally from 3 to 4, 4 is my right endpoint, so that's going to be all the way up here, and that's going to give me the height of my 4th rectangle. Okay? So if I were to ask you to draw it, this is what I would be looking for. You go to the right endpoint to get your height of your rectangle, and then draw it. So let's take a look at how we actually calculate this area then. So back to our subintervals here, 0 to 1, 1 to 2, 2 to 3, and 3 to 4. They're all equal subintervals. So all of these rectangles have a base of 1. And then we need to find the heights. Since this is a right estimation, we're going to find the heights of the right endpoints. Okay, so from 0 to 1, we want 1 as our right endpoint, and so we need the height at 1. So we can either plug it into our function here, or we could look at the graph. But 1 squared is 1, plus 3 gives us 4. Then we want 2, so 2 squared is 4, plus 3 is 7. 3 squared is 9, plus 3 is 12. 4 squared is 16, plus 3 is 19. All right, and we're finding the area of rectangles, which is base times height. And we already decided that all of these have a base of 1, so we're actually going to kind of factor that out. Because really we would be doing 1 times 4 plus 1 times 7 plus 1 times 12 plus 1 times 19, which in this case 1 doesn't really matter, but if it were a different width, we would want to have that there. So we're going to do 1 times 4 plus 7 plus 12 plus 19. And so we get that the area is 42, which means that the integral from 0 to 4 of f of x dx is approximately 42. All right, and we can see all of those rectangles go above the function, so I'm thinking this is an overestimate. All right, let's take a look at question 2. So for question 2, we want LRAM, so we want a left approximation, and we want 4 subintervals. So we're still going to do from 0 to 1, 1 to 2, 2 to 3, and 3 to 4, but now we want the left endpoints. So I'm going to go ahead right away and mark that. We want the left. Okay, so I'm going to draw it on my picture here. So from 0 to 1, I want my height to be whatever it is at 0. So there's my first rectangle. Then my second rectangle, I want my height to be at 1. So there's my second rectangle. For my third one, I want the height to be at 2. So I'm going to start at 2, go up and across to 3. There's my third rectangle. And then my fourth rectangle, I want my height to be at 3. So 1, 2, 3. And I want to go up to my function, and that's the height of my fourth rectangle. All right, so now we can actually see that this LRAM compared to the RRAM here, this is an underestimate. All of these rectangles are underneath my curve, so I'm thinking this number is going to be smaller. Okay, so let's see, my function at 0, so 0 squared is 0, plus 3 gives me a height of 3. And then at 1, I already know that it's 4, 2 was 7, and 3 was 12. Again, all of these subintervals have a width of 1, so all these rectangles have a width of 1, or a base of 1. So base times height, so we're going to get 1 times all the heights, the sum of all the heights, so 3 plus 4 plus 7 plus 12. So we get that the area is equal to, let's see, 26. So the integral from 0 to 4 of f of x dx is approximately 26. And you can see, I want to remind you guys, we're approximating this, we're estimating. Those numbers are really different from each other. All right, we didn't do anything wrong, but they're pretty different. And part of the problem with that is we have only 4 subintervals. We would need more to get a more approximate area. Okay? All right, let's look at MRAM then. So for MRAM, now we're doing a midpoint approximation, and we're doing 2 subintervals. So make sure you're paying attention to the fact that changed. So if I want 2 subintervals and I'm going from 0 to 4, that means I want to go from 0 to 2, and I want to go from 2 to 4. All right, so if I were to look at my graph, from 0 to 2, my midpoint would be at 1. So what I'm going to do is I'm going to go to 1, and I'm going to put a dotted line up to the function, and then that's what gives me my height of my first rectangle. All right, then I'm going to do the same thing. I'm going to pick a different color. The midpoint between 2 and 4 is 3. So at 3, I'm going to draw my dotted line up to my function, and that gives me my height of my second rectangle. All right, so looking at my picture over on the side then, I know my midpoint is at 1, and I know my midpoint is at 3. So I need the heights at 1 and 3. So at 1, my height happens to be 4, and at 3, my height happens to be 12. Now we do need to be careful here because the base is different now. The base of each of these, the width of my subintervals on both, happens to be 2. So both of these are a 2, and then I'm going to do 4 plus 12. So I get that this area is 32, which means the integral from 0 to 4 of f of x dx is approximately 32 when we use MRAM with 2 subintervals. All right, the trapezoidal one now. Let's go ahead and look at the trapezoidal. So if we're looking for a trapezoid, and we want 4 subintervals, so we're going to do 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Now with a trapezoid, we have to be careful. So let's look at what our picture looks like on here first. So I'm going to find my height at 0 and my height at 1, and I'm just going to connect those heights, and that's what makes my trapezoid. So really what I've done, and I'm going to make it a little bit more dramatic just to be able to see, but that's what my trapezoid looks like. So really I'm at 0 and 1 right here, so I have a width right here of 1. This happens to actually be the height of my trapezoid then. Alright, so I'm going to go ahead and put a little h there to remind us that's our height. And then the two parallel sides, those are my base 1 and base 2. Alright, so I'm not going to go ahead and draw all of those on there because this is a kind of a small graph and it gets a little squished. We'll talk more about it in class if we need to. But what that means is for each of these subintervals, I need the height at both of the endpoints because those happen to be my base 1 and base 2. So I know at 0 I have 3, then I have 4 at 1, and there's another 4. Then at 2 I have 7, and I've got both of them there. At 3 I'm going to have a height of 12. And then at 4 I'm going to have a height of 19. Alright, so we know that area of a trapezoid is h over 2 times b1 plus b2. Each of these trapezoids has the same height because each of these subintervals is 1. So what that means is for each of these, I can just make it a 1/2 on the outside, and now I'm just going to add together all of the bases. So I have 3 plus, I've got 2 4s, and then I have 2 7s, I have 2 12s, and then I have a 19. So if we go ahead and add all of that together, we'll actually get that the area comes out to 34. So the integral from 0 to 4 of f of x dx is approximately 34 when we use the trapezoidal. Okay, I know that this video is getting really long. I'm so sorry. We're going to do these in class. Okay, well actually I'm going to do one of them, but you guys can stop watching here. I just want you to have this as a video to watch later if need be. Okay, so these are actually easier because there's no calculating the y values. So if I want to do RRAM and I want 4 subintervals, and I've got these values here, my 4 subintervals are going to be 0 to 3, 3 to 6, 6 to 8, and 8 to 9. Now the important part here is to recognize that these subintervals have different widths. So from 0 to 3, I have a width of 3. 3 to 6, I have a width of 3, but here it's different. 6 to 8, I have a width of 2, and 8 to 9, I only have a width of 1. So that's going to be important when we start calculating our actual areas of these rectangles. Okay? Since it's an RRAM, I want the right endpoint, so I want the 3, the 6, the 8, and the 9. So at 3, my height is going to be 5, 6 is 4, 8 is 6, and then 9 is 8. So I'm going to go ahead and calculate that area. So the width of my interval is 3, and the height is 5. The width is 3, and the height is 4. The width is 2, and the height is 6. And then the width is 1, and the height is 8. So we can go ahead and get, let's see, 15 plus 12 plus 12 plus 8. So we get 47 for our area there. So the integral from 0 to 9 of f of x dx is approximately 47. All right, there we go. I promise you're done now. You should have stopped watching already anyway, but at least now you have one from a table where you can check, and we will do the rest in class tomorrow. I'll see you guys later. Bye!